interesting shit. It's like, not sold.
Anyway, so if you have turned in your homework, you know, I'll take a photograph, I'll take it till 5 o'clock, and I'll put up the answer key. I did write your homework last night, so I'll have it posted right at 5 o'clock, right when your last one is, right when I accept the last of your homework. And, excuse me, Cat was nuts on me last night. God, look at that. That kid, we got Beaver here. All right, so your homework is, the first two questions are a gas expanding, gas contracts. It's like isothermal, reversible, and I think I did 80 make it reversible. You gotta do DG, DT, DS, surrounding systems, blah, blah, blah. And then I have 8 questions of derivations, which, I mean, that's gonna be on the next test. So if you can work through those 8 derivations, there's nothing I can throw at you that you won't be able to answer. So that's good, right? And you know it's good. And those derivations are harder than the ones I'm gonna ask on the test. And I do, the derivation questions on the next homework, they rise in difficulty. So the first ones are easy and the last ones are hard, as usual. Anyway, all right, so we're used to that. I got your homework again. I haven't finished them yet, then turn it to me on Friday. Return it to me on 5 o'clock, or send me a photograph. If you haven't picked up your test, a lot of you asked me if you hadn't picked up your test. I have them right here, so I'll put those out at the end of class. Same old, same old. I don't think I don't really have much to say other than just go over new material. And we are largely going to go over this whole gas expands and gas contracts. We're kind of finishing that up. Actually today, we're going to largely finish it up today. And then we're going to do, not the gas expands and gas contracts, we're going to do a chemical reaction occurs or does not occur. And that's the next part of the class. And, geez, I don't really have much else to say other than to remind you that if you didn't make it last time, or if you never show up like Daniel never shows up, speaking to you, Dan, you wouldn't know him. His name is Dan. He never comes in. Anyway, last time the camera crapped out on us, and so I'm going to start with that bit that the camera crapped out because the battery ran out. Because, you know, I want you to all have this. I mean, it does seem to be a very useful thing to have the video. And let me start with there. Again, I'm always going to go over what I did last time. I spent like 10 minutes on it. Before I go there, questions. Are there any questions? You guys are pretty full of questions, which is great. If not, no questions. We're set. We're set? Okay, that's great. Okay, last time we went over, okay, yeah, I need to go over a couple things here. So changing U. Now, remember, we mostly went over those Maxwell relationships. Last time, obviously, many folks can't see. And I'm doing, look at this, I'm doing this from memory. I'm just going to do it from memory, because I can. And you can, I understand that. That's why this stuff is on the cheat sheet. All right, so Maxwell equations dt, blah, de blah, de blah. TdB of constant S is, sorry, my handwriting's not good today. Quantity P minus ds of constant B. And I wanted to point out to you that we did this guy before. That is minus B over CB. Now again, we did that on the extra Friday, last Friday. And then I have the H is TDS because enthalpy depends on entropy plus VDP. And then the blah, the blah, the blah, okay, dV, ds, ds at constant P is equal to dt, dt at constant S. Okay. Now the important thing about this, because it's on your homework, I got it wrong. On the last lecture. I just noticed that my notes were not incorrect. I accidentally got this flipped. So if you could, have some double check. Okay, it's on your homework. Blah, I'm just saying it, right? It's on your homework, and I got it flipped last time. And remember, I told you many times that you often see, whenever you have a constant volume, or you have volume or pressure, no matter what, volume or pressure, you often see a minus sign, and the V's turn to V's, and T's turn to V's. And I guess I already made a mistake. This is CP. CP. Okay, so P's turn to minus V's, and V's turn to P's. Sorry about that, already. It's like I almost threw it twice. Okay, changing A is, that's the one that's always negative, that's that's STT, minus STT, minus PDV. And again, I'm doing that from memory because I remember that A has the work dependence of U, but it has the temperature dependence of A or G. And from this, I get dS. dS dV at constant T is dt at constant T. There we go. And then I have UG. Okay, that's the double Legendre polynomial. That's minus SDT plus dDP. And therefore, d blah, 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 that's dV dt. The constant P is minus change in S, dP at constant T. Okay, anyways, this is again a review. Why are you writing this down? You don't have to write this down, you already wrote it down, except for the part that last time. So anyway, so this is the main thing from last lecture, and you do need to know it. You're going to begin all these freaking derivations. You're going to begin all the derivations with these guys, and you're going to do the derivations just like I did last time. And if you have some trouble, we'll work on that on Friday, so no problem. Okay, so you have these guys, which are important. Now you have to remember this one, you have to remember this one, but notice that from this I just did Legendre transforms in my mind. I got these, and these are Euler formula, which you get is on the cheat sheet. So you don't have to remember that either. And if you forget, remember I'm going to have the y, the f, the x, constant y, constant x. This is where it all comes from. I'm sorry for my sloppy handwriting. Doesn't matter. Okay, so this is on the cheat sheet. So if you get confused, and if I ask you to solve these, which I often do on tests, you have that. That's where it comes from. No problem. F's are U's or G's or A's or H's. X's or T's or P's or S's or D's, and there you go. No problem. Easy. So 3 points. That's how I can do that. Okay, so that's what I went over last time. That was on the homework. Screwed up, sorry. Anyway. So now, actually, new material. Sorry, let me go into the material that I didn't quite finish, which was not on the video, and that was that it's G, because actually I was filming a lot of things over the weekend. I was filming stuff that I do in my lab, and so the battery was run out, and that's why. So when we take the Legendre transform of U and get H, right, and that removes the V dependence on U and puts it on P. And so H is a friend. When P is constant, H is a friend because it becomes heat. Exterior heat, the heat given off. When P is constant, which is useful, and then we also Legendre transform out the entropy dependence, which I don't have an entropy meter, and we put it on temperature, and that's why G is special. So this is what we did last time. That's again a Legendre transform. And what we found was that G, T, P and constant P. Again, look, one of its variables is held constant, which again is useful. And then we found that minus S is G minus H over T. And then we ran into a really horrendous problem in that I can't, this and this can't do, because I have change in y with respect to x is equal to a function of y. Can't do that. Right, that's, well, if we had math 9, or, we had calculus 9, we could do it, but we don't. So instead, this ended up being kind of impossible. And then what I did was, and I'm just going to abbreviate because it's really not hard, it's in your textbook. Oh, most of you don't have your textbook. I wanted to point out. Yeah, that's funny. Anyway. So what we did was this. So again, unsolvable. Unsolvable. That's what that means. For Dan, who's watching at home every day. This is unsolvable, but this one was. And we used the product rule on this. And what we had was, what did we have? Let me remind myself. dt. We had change in G over T. Again, this is the product rule. And pretty much, yeah, this is what I meant to put in. So we have this guy here. Sorry, I should have put this in. Yeah, it is important, right? In this case, it's not, but generally it is. So anyway, I have this here. I insert that, and then what I end up with is minus h over t squared. So Dan, since he didn't come in yesterday, or Monday, here you go. And remember that this is, because we're getting into this on Friday, we're going to talk about A plus B goes to C plus D. And if this reaction is going to be spontaneous under constant temperature, constant pressure, which is the only conditions that matter, then this G has to be less than that G. G plus G is less than that G plus that G. And then we have to think about, like, okay, well, it's not, so what do I do? Well, do I raise or lower temperature? Again, this doesn't matter. This is divided by T. It doesn't matter because it's always positive. Doesn't matter. Well, it depends on the enthalpy content of H and, of C and D. If these guys have higher enthalpy content, is it good or bad to lower temperature? Sorry, let me raise temperature. That's more sensible. Again, I can measure this. I can measure the enthalpy content. I can measure H of C and D. They're gases. They're liquid. Whatever. I can measure their H. I can measure their U. I can measure their G. I can measure their A. All right, so I have the H of C and D, and I have the H of A and B. Again, these are just things that just make a measurement with a calorimeter, which is something I'm going to get into today. All right, so if this reaction is going to go, and C and D have higher H, do I heat or do I cool?
Cool.
I have to think about this. All right, that's, if that's true, then H, think again, I think you got it wrong. All right, this is a big number for C and D. It means that if I increase temperature, if I increase number, their G gets smaller. Right, is that good or bad? Now, remember, we're doing this because we want C and D. We don't want it to go in reverse. Why the hell would I do this to begin with? We want C and D. Again, delta G on negative delta G is good because we want C and D if C and D's G's summed together is less than A and B's. Now, their enthalpy is higher. Do I increase or raise temperature? I'm a little out of it. Do I increase or decrease temperature?
Increase.
You increase temperature, right? Because if this number is higher, then if I If that increases higher, then this is a bigger negative number, because temperature is always positive. I'll give you a break, all right? I'm kind of so this is a bigger negative number if these guys' H's are bigger, and that means if I raise temperature, G goes down faster. Smaller number minus a bigger number is a negative number, and that's what I want. And don't forget, I'm sorry, I know I'm kind of now in a crazy world here. Remember that in the Clausius inequality, that we know that we want G to be negative because we multiplied the Clausius inequality by negative temperature, as you did on your homework on the last, on number 9, right? Or 10, what, who cares? I don't care. I'm not even going to grade it. Everyone gets an A. No, that's not true. Anyway, so again, you want G to go down, and it depends on the enthalpy amount of C and D versus A and B. Okay, anyway, I'm still yappering my mouth. Also note that Eg as a function of pressure at constant temperature is volume, and therefore Eg is PdV. I'm sorry, VdP. What's wrong with me? Okay, so there you go. And that gives you a solution to solve for delta G. As you're going to do on the homework, because I have you solving delta G for a gas expands and gas contracts. And let's see, this is nRT over P. And then when we integrate, delta G is nRT ln PF over PI. There we go. Hopefully that's correct. And this would be at constant temperature. Okay, funny thing. So now you have delta G, and delta A is the same. Let me just tell you, this is also delta A. So there you go. That's how you answer your homework question. Damnedest thing is that I can't do this under adiabatic conditions. I can't do this under adiabatic conditions because that because basically why can I do this? So I did isothermal. Here, let me just. Sorry, I'm kind of freelancing right now. I just realized I never really explained this very well, so I'm kind of going off my notes, so I'm sorry if I'm a little wonky. So this is dG, and I said isothermal, so that term disappeared, and it left me with this term, which I can solve. There you go. And so when a gas expands, a gas contracts. Easy. Points. Gimme. A's. Right, no problem. And this is actually going to turn out to be the same for delta A. It's going to be the exact same thing. The problem is that when it comes to adiabatic conditions, this is true, right? Adiabatic conditions have temperature changing. And the problem becomes that I have to know the absolute entropy. So knowing pressure and volume of a gas is easy. I give it to you. It's sensible. It's a balloon. I can blow up a balloon. See that? I can blow up a balloon and I can blow up a balloon and know V and P. I can know that. But when it comes to T, I can know that, but S, I don't know that. That's hard. So when it comes to adiabatic conditions, it's a subtlety. I will never ask you on an adiabatic reversible, irreversible transition to ask you G or A. Because it requires the absolute enthalpy. Enthalpy. Did I just go twice? Entropy. It requires the absolute entropy, which is known. But I don't go. Anyway, so when you have an adiabatic reversible, irreversible, I never ask the G or the A. It's because you have to know that, and screw it, it's too hard. So anyway, that's just little funny things to look out for. Well, hot damn, folks, that's it. That's a gas expands, a gas contracts. We're done. completely done. Oh, we're not done, except you're going to see it on your exams, on your second exam and on your finals. But I don't really have much else with gases, so we have to get to real substances, real liquids, real solids, and we have to start talking about how they actually react and whether they react. And unfortunately, this is something that, oh God, I just love this part of this class. You've been lied to. He's cheating on you. No, just kidding. You've been lied to. We lied to you again, as you've already seen once or twice. We've been lied to because we tried to make things a little too simple. And because we tried to make things simple for you so that your little brain's like, my little kitty, so that my little kitty can process it, we've told you a simplification of the truth, but it wasn't ever really true. And I really have mixed feelings on this. We got you to subtract G of products minus reactants, is that right? Yeah, it's wrong. I know that's what we told you, I'm just telling you. No, that wasn't right. We told you that because it was easy to do, easy to process. It was never actually true. And let me tell you this. Again, I'm going to go off my notes because I'm being an idiot today. Okay, so G of, we had A and B and C and D. I've lost weight, yes, I can jump higher. So I have G of C and D, and I add those and I subtract the G of A and B. And you look those up where? Where did you find them? You have a book, where? I have a book, and then I do what with the book? Look in the back, right? There's a table. There's a table in the back of the book with G's. G's of formation of C and D, and then I find the G's of formation of A and B. The thing is, here's where one of the greater subtleties is. That's for pure C and pure D and pure A and pure B. Now, if A and B are going to react to form C and D, are they pure? I have A, I have B, I want them to react. What do? Mix them. Right, I have to mix them. So does that delta G apply anymore? No. No, there you go. The answer is no. When you mix things, that G that you got in the back of the book is no longer correct. So even before anything even freaking reacted to begin with, that G of A, B, and C, and D, all those G's are wrong. They're all wrong. And you have to make corrections, and that's what I'm going to show you how to do. So anyway, so that's where we're heading. I'm not going to quite get into A and B and C and D quite today, but we're going to get there on Friday. What I want to do is go over the third law. Why not I write the first law? Just to remind you, energy is neither created or, oh God, my handwriting's awful, destroyed. Okay, in case it's on your final, which it is. Right. RateMyProfessors.com. Okay, this one is that total entropy always increases, or, oh God, that or, that's, or, can't turn to all work. Okay, two statements of the second law. We have the Clausius statement, which is this, you can't turn all heat to work. And then we have the statement that you kind of learned a long time ago, which is your instinct, which is that entropy always increases. Buildings always fall down, cats always scratch, especially a little bitch. I mean, anyway, so then we have the third law. Oh God, my handwriting is awful today. Sorry about that. Third law. And I already told you this once when we were talking about the total entropy. Oh, excuse me. And this is from it's called the Nernst. Let me make sure I spell it right. Nernst theorem. And I don't know why a law is expressed by a theorem. I just did the opposite, but anyway, I don't get that, but whatever. These are things for philosophers. And that is a perfect crystal. So I'm going to use a little shorthand. Perfect crystal at 0 degrees K has 0 joules per K entropy. Okay, so that's the third law. Write it down, don't write it down, whatever, watch the video. Yes, I'm going to follow, but anyway, so this is the third law. And notice that the third law, I mean, I've never been a big fan of the third law. Not like I'm a fan of Justin Bieber. I think that this just says that the second law is correct, because what it says is, as I'm about to show, is that the third law simply means that entropy is measurable. I'm going to explain that in 1 second. It means entropy is measurable. If something is measurable, it's real. If it's real, then the second law is correct. Meaning that the third law just says the second law is correct. I said that before, but now you see why. And oh man, who cares? Anyway, so let's do this. Let's write entropy as a function of temperature. And in the big scheme of things, entropy is a weird guy. Entropy has always been the bane of our thermodynamic lives because I need to know what it is, not what it's relative to. So when it comes to delta G, G, look at the top. I'm talking about G. Everything has a G content. This thing has a G content. It has a U content. It has a U content defined by the equipartition theorem. And then I can measure its pressure and volume. And then I know its H content. And then I can figure out its A content. Then I can figure out its G content. And then I can figure out how much energy is released when I react it with oxygen by burning, which is what you're going to do after this class. What happens when I burn it? And then I know the CO2 and CO2 and H2O, and I know paper and oxygen on the other side, and I know whether that reaction is spontaneous or not, which it is. All right? But when you look in the back of the book, remember I just reminded you this a second ago. When you looked in the back of the book, you didn't have G. You had G of formation, delta G of formation. And what happens is that when we tabulate, which we're going to get into on Friday, when we tabulate G's, we did not tabulate absolute G's. We tabulated delta G's of formation. Delta G's of formation of things, paper, cats, water, methane, hydrogen, from their elements. When we tabulated delta G's, we didn't tabulate G's themselves. It's different. But when it came to entropy, we had to calculate the absolute entropy, not the change in entropy for a formation. And I'm going to get at it. This is a little bit confusing. That's okay. I'm going to explain more on Friday and Monday. When it came to entropy, we had to calculate the absolute entropy of substances because of that term up there, that minus SET, that appears in A and G. We had to calculate the absolute entropy. And that sucks, but we did it. Actually, the engineer did it. Thanks for doing that. I didn't have to do it. So, what that is equal to, again, the reason we had to do this is because of that entropy term up there. It's not something I can take as relative. Now, remember, this is a function of temperature, so I just said that's OCD, so that's S of 0K. And remember, I just decided that was 0 joules per K. Right, that gives me a starting point. That means I can measure it. Again, the third law proves the second law. Okay. Now, funny thing, that this is, okay, the Q over T will change in S, right? And as long as you're reversible, we'll measure this reversibly. And, okay, now I want to think practically here. Now I know that I've done changes of heat in terms of heat capacity at constant volume. Now remember that I've got a substance that's at 0 degrees K. It's a solid, liquid, gas? It's obviously solid. So, am I going to measure heat with CV or CP? There you go. Because again, it's really hard to keep a solid, to measure its heat capacity, to measure, the way this works is you have a bomb, right? Now, you've done this before. You have a bomb, which is just a canister, a metal canister. You have a material inside of it. You measure the heat that goes into it, and you do that electrically. Because our ability to measure electricity is very good, because electricity is an old science. So we measure the amount of electricity that goes into the bomb, and then we measure the heat rise of the bomb, which we can do quite well. Okay. But again, we can't really keep a substance, especially a solid, at constant volume. At best, we can keep it at constant pressure. That constant pressure is easy. Constant volume can be done. It can be done in some cases, but not easy. But so anyway, so this is one of those times that you have to use CP, EP. Is that right? Am I missing?
Over T.
Over T, that's right. And we're going to get a natural log, but anyway, again, this is data easily taken, and we're going to, of course, integrate that. This is 0, so it doesn't matter. 0K to, okay, so IUPAC, again, I'm a big IUPAC fan. The temperature at which something melts is the fusion temperature. There you go. That's what it's called. Fusion temperature. It's actually the temperature at which a liquid melts to a solid, but IUPAC doesn't care. So it's the same thing as when a solid melts to a liquid. And now we have to consider phase transformations, and we have to consider the fusion enthalpy. Again, the solid must melt, and it must take heat to do so. And of course, it does so at the fusion temperature. There you go. So that's like a static jump in the entropy. And then we've got, again, we've got a liquid now. So now we've got the fusion. And then we've got the vaporization. We've got this term. And on and on and on. Here, let me, I kind of screwed this up. Let me add a term. I normally stop here, but just so you know that this just goes on and on and on. You take the vaporization, H, of something, and divide that by the temperature. And then, of course, you stop. Then, of course, you can consider the heat capacity of the gas at constant pressure, constant volume, it doesn't matter. In any way. So this is how you calculate the absolute entropy of a thing, of anything, of a cat, of a gas, or whatever, or borax, even, borax. But anyway, so, and of course, what we do is we calculate the entropy of things at, guess what temperature? Look in the back of the book, the temperature is at
25 Celsius.
Yeah, 25 degrees Celsius, right? So what you engineers did is that you took every fucking thing that you can get your hands on, you put a mole of it in a bomb calorimeter, and you froze it. I kid you not. You guys did this, or your grandparents did it. You took everything that existed that you could get your hands on, and you froze it to 0 degrees K, you warmed it to room temperature, and you measured the heat that went into the system, and going, and again, heat and heat capacity are the same thing. So you had this, and you measured the absolute entropy of everything that exists, which was quite an effort, but you did it. And that allows us to do all the thermodynamic chemistry that we've ever done because we measured it. And that will be more apparent later on. It's not a big deal right now, it will be a little bit. Let me draw you what this looks like. This is going to come up in 346. And I know I said I was going to do some 346 stuff. I am going to prepare you for that, but maybe after the second test. After the second test, the third part of this class is really kind of dry and boring. So like we talk about like liquid mixtures, it's not really fun. I don't find it fun. So, and there's not really a hell of a lot to talk about in terms of actual content. So that's when I'm gonna maybe diverge and start helping you, getting ready for 346, because God knows that's more important. And this is one of those times. All right, so this is very much a 346 deal. So entropy versus temperature. What I'm doing is I'm integrating this thing right here. Now, for almost all materials, it does this. That is a S is proportional to T to the third power. That is almost universal, except for metals. So just remember that. I'm going to explain it further. All right, so it does that. It goes as T to the third power, so it rises sharply. All right, then entropy tends to level off. Sorry, that's kind of ugly. Then, rises, then we get to the fusion temperature. And there's a sharp rise, then it rises again. Then it gets to the vaporization, and then it rises again. Sorry, I ran out of room, that's stupid, but anyway, you get the point. And then, of course, it turns into a plasma, I don't know, whatever, who cares, but that's the idea. Now, here's the damnedest thing. T to the 3. And again, a little history, because history is good. History, it's entertaining. Entropy, again, at low temperatures, and especially this guy, Joke was his name, it's spelled Giaque. G-I-A-Q-U-E is how his last name is spelled, but it's pronounced Joke. Like a Frenchman, it's a joke. That was so nationalistic. Anyway, so Joke actually had a building named after him where I used to work when I was at UC Berkeley. Joke was the guy who got low temperature refrigerators to work with liquid helium, because your average refrigerator gets down to minus 20. If you get a refrigerator on steroids, it can go down to minus 80, but to get down to minus 270, you need a helium refrigerator. And this guy Joke, he was he got it to work with helium as a refrigerant, and he won a Nobel Prize for it. And so Joke was able, again, he won a Nobel Prize because he was able to do this part of the measurement. Again, he measured heat capacities with the Nernst theorem, giving him a starting point that is measurable. He was able to cool things and then measure the heat content, which gave him the entropy, and he was able to generate these curves. And he saw T to the 3 dependence. Now, okay, explain it, right? Now, so the experimentalist takes the experiment, it generates the experimental data, the theoretician comes up with an answer, like Albert Einstein. Albert Einstein, no one can describe this. No one can describe this behavior. No one can do it. Albert Einstein, being Einstein, he said, "Well," he comes in the room and says, "Well, I can solve this." And he did well. He did well. It was kind of like this. Kind of like that. I'm sorry, that's not perfect. And he said, I'm keeping it together. So he definitely did a good job, but it wasn't right. It wasn't right. And everyone knew that his theoretical description was wrong. And along comes, it was Debye, Peter Debye, who, let me see, I'm going off my notes again, as I always do. Peter Debye said that heat capacity, again, we figure entropy by heat capacity. Heat capacity, constant pressure, constant volume, doesn't matter. It's it's degrees of freedom, right, that's U. And that works at constant volume, but it's still the same idea, look, it all works. That's the idea, is that the degrees of freedom are being thawed at these low temperatures, and these rotations and translations are absorbing more and more energy. And so what Debye said, so degree of freedom, what Debye said is that the degrees of freedom versus temperature does like this. Again, it scales as t to the 3. And you don't have to write this down, by the way. I'm not going to be testing on this. This is one of those times I go off on a tangent, and I just want you to know how stuff works, right? Because it's kind of important. And maybe it's not to you, but whatever, you're here, so you're stuck. Anyway, so Debye said that degrees of freedom are absorbing this energy, and the more degrees of freedom you have with temperature, the more you're able to absorb energy. But it comes to a cutoff. It comes to a stop at some point. That's when you run out of rotations, right? You know, translate, 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 rotate, 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 vibrate, no, no, no. That's what I said to my cat last night. No, no, no. No vibrations, right? So you're freezing out these translations, you're freezing out these rotations, but you come to the next degree of freedom, which is vibrations, and the vibrations quantum mechanically take too much heat energy, and they don't kick in until like way out here, which is something that we just don't do. He applied his theory to this, and he nailed it. I should use different colored pens. He nailed it. Debye nailed it. This is often called the Debye. The Debye temperature is when you cut off the number of degrees of freedom for, water, cats, chickens, whatever this is. And anyway, okay, I've talked way too much. Let me go just one more little bit thing. So why was this important? What does this mean in terms of 346? Again, it was because of quantum mechanics. See, Debye was this close. I mean, you've heard of Peter Debye, but he's not as famous as Erwin Schrödinger or Heisenberg. Not the guy who sold meth, all right? The other guy. I like the other guy better, but I like being referred to. But anyway, so Peter Debye was almost that famous because Peter Debye, when he did this, he discovered quantum mechanics, but he didn't realize it. So the issue is that because of quantum mechanics, because there's certain energy levels, because energy is not continuous, energy comes in spurts. It comes in these giant steps. That's why you have this cutoff. You hit a step that you can't cross. And Debye figured that out. He just didn't know why. And Schrödinger and Heisenberg come along and say, that's because everything comes in energetic steps. Eventually the steps get too big and you just can't cross them anymore. And that is quantum mechanics. And Debye didn't realize that. So that's why Debye is not as famous as Schrödinger or Heisenberg. Now Einstein saw this and called Debye wrong. I just thought that was funny. Yeah. Einstein did not believe Debye was correct. And he told him, he said, you're an idiot. He said, God does not play dice with the universe. And the thing about quantum mechanics is that it's a science of probability, not a science of absolutes like S is equal to this, S is equal to probably this. And Einstein said that's wrong. And so this is really funny. Einstein ended up coming up with an experiment. He said, if you quantum people, if you Debye people are correct, here's an experiment you can do. And if it works this way, then you're right. If it works my way, then I'm right. Guess which one happened? It's called the EPR experiment. You can Google it. It worked in Debye's way. And so it proved, Einstein proposed an experiment that he thought would disprove quantum mechanics. It ended up proving quantum mechanics. So anyway, Google EPR experiment. It's kind of fascinating, and even YouTube has some really nice little videos on that. So anyway, so that's why this is kind of important to prove quantum mechanics. And anything else I want to say? No, in all honesty, why don't we end a little early today? God knows I thought I have your old test. Have your old test. Give me your homework if you don't have your homework. Have your old test. You just pick them up. So it's right here. And I will see you on Friday. God knows we're going to have a good time then. So pick up your homeworks if you haven't, especially Daniel, who hasn't picked up a damn homework yet. And I'll see you all on Friday.